Hello, my name is Oliver Markowski, and today I'm going to show you how to do 3D Gaussian ray tracing inside Houdini Solaris. So, first things first, what is a Gaussian? A Gaussian is basically just an ellipsoid that has a transparency falling off from the center towards the edges. So this video is going to be two parts. First part is how to get the instancer working, and the second part is the shader. So first of all, what are we going to do? We are going to simply instance a sphere onto a point cloud. And the point cloud is what you get from any training of either your own data or from the internet. So in my example that we are using here, the point cloud is taken from repo-sem.inria. You see that? I'm going to put it into the description of the video so you can download the pre-trained models yourself. The model I'm using here right now is the garden. So, as you can see, there's just a shit ton of points, and you can kind of guess that there is going to be the table and everything, but it's just points from this PLY file. These points, they have also a ton of attributes. These are basically the spherical harmonic coefficients for all the certain degrees. It's a lot, as you can see. Then we find opacity, rotation, and scale. And wouldn't it be easy if you could just use all the values just as is without any tricks? Yes, it would be, but if that would be that easy, you wouldn't be watching this video. So, how do we use this data that is on the points? First, color. That's easy. It's at least the non-view dependent color, basically spherical harmonics degree 0. This is how you get like a base color that is not view dependent, obviously, but it does the trick to like for 90%. How do we do that? There is on the GitHub page of the initial implementation, of the official implementation of 3D Gaussian Splatting. You can just check out this link. I'm going to put it in the description as well. You find a Python file which is called shutils, sh for spherical harmonics. And to get the first degree of the spherical harmonics, you just modify the constant 0 or constant for degree 0 by whatever coefficient you have for degree 0. So in this case, C0 is a constant, as I said. All the constants are defined in this Python file. You can find them on the web as well. So what you do is just you take constant 0 and multiply it with the coefficients for constant 0. These are for red, this is f underscore dc0. For green, it's f underscore dc1, and for blue, it's f underscore dc2. Of course, there's a little catch. You have to, in the end, add 0.5 to the result, which is also part of this evil sh function. You can find it all the way at the end. If you want to go sh spherical harmonics to sRGB, basically this is what I'm using. You just add 0.5. And that's what we do. So let's see what the result of this. Click, and voila, you have color. Then you just turn off Open Color IO because the colors in here, they are already Rec 709 gamut and already gamma corrected. So this is not, we're not in ACES land yet and all that jazz. This is probably for a later video. For now, I'm just gonna go like straight through the rendering pipeline without any color space transforms and stuff that you would do in a high-end VFX production. So now we have color. Amazing. I guess you could have figured it out yourself because that's the easy part, to be honest. But now here comes the catch. And this is where another website comes into play that I'm really, really thankful of. It's the blog from whoever the user 42yeah is. But I'm really thankful and I highly appreciate his work. And I'm gonna link this page for you as well. On this page, I found out how to convert the opacities that are stored on the points to an actual usable alpha inside Houdini. And to do that, we need to make use of a sigmoid function as shown here. And you just run your opacities through that function, and with the alpha you're basically already set. If you use the variable alpha with an uppercase A, this has the added benefit that Houdini understands that out of the box. The second thing I learned from this website is how to get proper scale values that are usable in the point instancer. To convert the scales on the point cloud, you just run scale 0, 1, and 2 through an X function and you're good. Of course, you can see at the end there I multiplied by 2. I don't have a clue why that is. Also, the dude on the website doesn't have a clue. He just said I did it and it worked, so that's what I did. If you know why that is, feel free to tell us in the comments. I'm always eager to learn. Now to the final boss of my research, which took me quite a couple of days to figure out what is going on there, is the rotation or orientation that is stored on the points. You cannot use it directly on the point instancer. So if you just use the order in which they are stored on the point cloud and say 0, 1, 2, 3, and you get completely wrong orientations. What you have to do is you have to put them in the order 1, 2, 3, 0. And again, I figured this out using ChatGPT, where I asked it, I have this line of code. Can you please provide me the same line with all possible combinations of the rod values? So, first try of ChatGPT wasn't very successful because for some reason it introduced rod 5. So I told it, you just invented rod 5, which wasn't there before. Please only provide all combinations of rod 1, 2, 3, and 4. And here we go. So I took this code, copied it, and just pasted it into the Wrangle, and then I started commenting out every single line until I was successful and I found what you see here. Obviously, this is what you need, but nobody tells you why. And I tell you why. Because quaternions are typically represented in two common formats. W, X, Y, Z. This is the most common representation in the mathematical literature. In this format, W is the real scalar part, and XYZ are the imaginary vector components. XYZW. Some software packages, including certain graphics and 3D applications, use this order. This is sometimes called the vector-first representation, where the vector components XYZ come first, followed by the scalar part. Thank you. Now you know. It took me days to figure this out. You're welcome. With this problem solved, we have more or less concluded part 1 of the 2 parts, where we now have properly oriented and scaled ellipsoids. And next up is the shader part. If you like what you saw so far, then please leave a like now. And if you want to see more content like this, please follow and subscribe to my channel. Highly appreciate it. And now let's get to the second part, the shading. Here's what I asked ChatGPT. Given a random 3D vector, what is the easiest way to calculate the distance of the intersection point of this vector with a 2D plane containing the origin that is perpendicular to this vector? Then some blah blah. Then it's some Python code, which is great. Some more explanation. You can pause the video anytime. Then I had to tell ChatGPT that the 3D vector doesn't start from the origin, so it updated the code for me. And then I told it, can you please add code for plotting? So after that, I did some refinement for that code for the plots and stuff. I asked it to add the origin. And what came out of this, you could just straight away copy into Visual Studio Code, hit play, and here we go. So there's a random vector. Here's a plane. Black is the origin, 0, 0, 0. Blue is the intersection point. And so origin is on the plane, intersection point is on the plane, and this is origin to intersection, basically the length of, or the distance of the point to the mean or origin or center of the ellipsoid. So now, given this code, you can take away the, or you just can use this and implement this as a MaterialX node graph, and that's what I did. So it's not too hard. So let's see. In Houdini, we go into our material library, but let's first just visualize the plain colors of this. So I have prepared 3 different shader examples. Shader example number 1, this is basically giving us the plain colors. So nothing fancy here. You can see this is actually really fast because there's not much opacity involved, and so this is still okay for a path tracer or ray tracer to do, but obviously this doesn't look real. So we need to add the opacities and the Gaussian distribution function to all the ellipsoids. So you can see my 2 spheres in here. They're both mirrors. I could make one refractive, but that's not for this video. It's just you can trust me. This works also in refraction. So material library. What we do is first of all to get the color only. That's easy because we have that pre-computed on the all the instance points as a property or primbar called display color. So we just read display color and pipe it straight through. This is again not supporting view-dependent spherical harmonic based colors. I'll get to that later, and I'll tell you later why it doesn't work for me yet. Yeah, let's do the other stuff first. So this is just color, easy peasy. And next is visualizing the opacity, what I just showed you in Visual Studio Code and Matplotlib. So basically, all my ellipsoids are now getting a constant gradient from 1 to 0. It's actually not 0, 0, because this is in the nature of the Gaussian distribution function, because this basically never reaches 0. We just have to cut off at one point, which is fine. And also the 3D Gaussian Splatting algorithm does it. It cuts off at 1 divided by 255. So it's somewhere around 0.003. This is where the thing just outputs 0. And it's part of my shading network. So what are we going to do? So first, a little bit of a disclosure. I'm using Gamma ray imports here for ray direction. This is meanwhile like supported directly from MaterialX view direction. So this is here. We could just swap it and be good. I'll just leave it in here for now. But what does not yet work in MaterialX, but hopefully will, is getting the ray origin, which is essential for getting proper reflections. You could get the ray origin for like the camera ray by just transforming the vector 0, 0, 0 from world space to camera space. This would work for camera rays, but it will not work for reflections. Basically, the two spheres in here. Once the camera ray, the primary ray, hits the sphere, the origin will be updated to be the hit point on the sphere. And from there on, it will trace somewhere else into the scene, and every other call to this shader will then have the origin set to the hit point from the camera ray for every other ray def, for every recursion. So this is kind of the only thing that is right now missing in MaterialX that prevents this from being like completely render agnostic. For now, we have to live with it. If you use Arnold, V-Ray, whatever, you can just basically rebuild this shader with the vanilla nodes of your favorite render engine. V-Ray just recently announced, or Chaos, my friends at Chaos, Vlado, has implemented 3D Gaussian Ray-Tracing in V-Ray, but still what I heard is this is not supported in Solaris and the Hydra delegate of V-Ray yet. So it's probably going to come in the next couple of weeks. The folks at Chaos are really fast in implementing user requests. So I'm really happy to see some movement in the direction of 3D Gaussian ray tracing, also from like commercial packages. And of course, Vlado, if he implements something, he's going to do it properly, not the way I did it, because my implementation is still a little bit flawed. You will see later, but it gets the job done to like 99%. So back to the actual implementation. So we need the ray direction, we need the ray origin. I'm transforming everything into object space, because this way I don't need to query the actual position of the ellipsoid, because, or the, not the position, but the mean or center of the ellipsoid, because if we transform everything into object space, then the center of the ellipsoid is at the origin. So we can just skip this part. Also, if we transform to object space, we don't have to normalize anything, because the spheres are already kind of unit spheres in object space. So we get a lot of this stuff for free. So in here, there comes the first dot product. So you can see the intersection distance. This is where we that we got from ChatGPT. Intersection distance. We do the dot product of the actual vector v. This is v max squared. So that's this part. Then we have the dot product between v and p0. We have to negate this and then divide it by this little guy. So we do the dot product, then we negate it, and then we divide. That's it. And after that, we just say p0 plus t plus v. Now that we have p int, last thing we need to do is calculate the distance by just taking the magnitude of this vector. And it's pretty straightforward. There's a MaterialX magnitude node where you just feed that in. And this gives us a radius, or the distance in object space, which is from 0 to 1, coming from the center of the Gaussian, goes towards the end, or towards the borders. Next, we have to run this distance through the modified Gaussian probability distribution function. This is basically e to the power of minus 0.5 times k is 5 in this example, times r squared. So what we do is we do r squared, then we do the times negative 0.5 times 5 is k is 5. I found that my results looked a little more visually pleasing using a higher k number. So in my case I used 7 or 8 when I did some tests before that. In here I just used the 5 to show you what it looks like using the same values as the original implementation, and then you run this through a MaterialX exp node and feed this in as the exponent. What this gives us is what you saw previously, is basically a inverted map, but with a Gaussian fall-off, more or less. That's really important, otherwise you don't get the same results. Now, again, there is still something else. There's another opacity involved, which is on the points, which is this display opacity, that we have to multiply this gradient with, just with the simple multiply node, then run this through the cutoff, more or less, so where we say, hey, everything below 0.00139 0039 will be black, and after that get something like this. And once we have that, we just combine both the display color and the opacity in the final shader, more or less, where we put the display color in the emission color and the opacity in the actual opacity, and not like we did in the visualizer in the emission color, like here. So you see this is plugged straight to the final shader. And if you plug this and have Karma compile, then you will see, ta-da, there is your 3D Gaussian ray tracing beauty image. You can, of course, scrub through the timeline to see what happens. Again, there's no view dependency. The part of the view dependency I will cover in a follow-up video. You can see this here. All the code you need to implement this yourself is already in the eval sh function and the GitHub repo from INRIA. So just implement this stuff. Like you have the constants and the coefficients, and then you just multiply, add or subtract the shit out of it. And this is kind of what I came up with here, but I already got stuck at degree 1, where I could not make the first degree look like it should. I triple checked everything I did here, but for some reason it introduced a color shift towards like a blue. It got a bluish tint, which is completely wrong, and I'm still trying to figure out why. So this video only covers the degree 0 that we have pre-computed, which is also way faster. I don't know if you even need that to integrate CG objects into a Gaussian splat or a Gaussian ray tracing setup. Yeah, and that's pretty much it. I hope you liked the video. And all I have to say is thank you and much love to all you geeks out there. See you in the next one.